So a LDR and a thermistor are basically resistors, only they're a little bit more than a resistor. They behave like a resistor, but but it is dependent on the environment, how the resistance of these LDRs and thermistors are dependent on the environment. This is a symbol for a fixed resistor, and as I showed a moment ago, to measure the current, we just set the ammeter in series. To measure the voltage, we set the voltmeter across. So before and after, we were trying to measure the difference in energy per charge between 2 points. This is what a voltage is. And so energy is given to the electrons by the battery, and then as it goes through the resistor, it loses that energy between this point and that point. The current, it always flows from the small line to the big line, so it's doing this. Technically, it does split up here, of course. That's a junction, so it goes in two places. But we don't tend to think of the voltage as part of the voltmeter as part of the circuit. And so we would still call this a series circuit. Okay? The voltmeter is actually in the circuit, but we kind of pretend it's not there. So that's how we would measure the resistance of this resistor if we didn't know what the value was. So I will actually, before I talk about thermistors, I'll talk about one other type of resistor, which is a variable resistor. A variable resistor has a line through it, a little bit like a thermistor, but it's an arrow. Now, this is a variable resistor, which means it can be varied, but this means it is controllable by me or you or somebody who used it. So in other words, think about a dimmer switch. Nowadays, more and more people are having smart bulbs nowadays. But if you've got a dimmer switch at home, like an old-fashioned dial which you turn down and turn up, you can control the brightness on your light. But also, maybe a normal one would be a volume control and a sound system. You turn it up and down. These will be these will be variable resistors that are controlling it. So as you increase the resistance, the brightness of the light bulb goes down, or the volume of the sound goes down. So that would be one use of a variable resistor. If it didn't have the arrow, like you saw a moment ago, that's a fixed resistor. So the value of that resistor stays the same, or should stay the same. Now, what a thermistor does is the value of the resistance changes dependent on the temperature of the thermistor. So now, generally speaking, you will have a negative temperature coefficient thermistor. So that otherwise is just called an NTC. It was just thermistor, sorry. Whoops. Now, I can't move that. There we go. So that stands for negative temperature coefficient. Now, most likely, you won't see this. It'll probably just be called a thermistor. But so generally speaking, probably maybe all the time, whenever you see the word thermistor, it means NTC thermistor or negative temperature coefficient thermistor. You don't need to know what coefficient means. You don't in fact need to know what any of this means exactly, apart from the whole thing altogether means something that when it is, let me get this right, when it's hotter, so when the temperature increases, then the resistance decreases. Now, the thing that's interesting about this is that the exact opposite happens for a regular piece of metal. So earlier on, I said a fixed resistor should have a fixed value, right? Just trying to get a little arrow here, right? So if we have a A bit confusing. We've got lots of arrows here, but hopefully you realise that basically what I'm trying to say is that increase in the temperature causes the resistance to go down. That's for a thermistor, for more accurately, a negative temperature coefficient thermistor. I'm just going to copy that, put that there, maybe make it a bit smaller. So this is what you'd see for for this situation. And for regular wire, what happens is it actually gets as the temperature increases, the resistance increases. So this is what's strange about it. We won't talk about why regular wire gets and the resistance goes up at the moment, but it normally does. But the opposite happens for thermistor. Briefly, the reason why is because the material that a thermistor is made out of is something called a semiconductor. Semiconductors, if you think about what the name is made out of, semi means, well, half. Conductor means it conducts electricity in this case. So a semiconductor sort of conducts electricity, but not completely. And one of the things that can happen is that if you change the situation, it can cause it to conduct electricity more. And actually, with semiconductors, when you heat them up, they actually they're able to conduct heat more easily. I won't go into the reasons why at the moment. Now, an LDR, this time what happens, and I've got to make sure I get this right around. I'm pretty sure that if you, okay, it doesn't tell you right here, but I'm 95% certain that what happens is it's the increase of light that reduces the resistance. But maybe we can find out this in a moment. Now, so this whole section is really, so far in this page, apart from what I've talked about, is talking about how you would investigate that. Really, it just means set it up as shown in the diagram, and then what we can do is we could change the conditions and measure the voltage and the current, and each time work out what the resistance is. So we could, so we've got a heater with a dimmer switch. So in other words, you can change the value of the temperature and measure the voltage and the current each time. What is the voltage and current when the resistance when the temperature is this? What is it when it's that? And so on. And you can see what's going to what are the values, what happens to the resistance when you change that. So what's the relationship? So you might have temperature, voltage, current, resistance. This one is calculated, and these two are measured, and this one is changed. So, and you decide whether you go 30, 40, 50, 60, or 30, 35, and so on, 40. So that's when you are writing about this and designing an experiment, make sure that you include what you're going up in, what's the range of your temperatures, what are you measuring, how are you measuring it, and so on. So make sure, for example, to mention that you're going to use a thermometer. There's no mention of a thermometer in this experiment. In this case, you can do what we call a qualitative, in fact, both cases you can do what we call a qualitative investigation, where we just say, well, as I make this hotter, then the resistance goes down. A quantitative one is actually giving the values of what the temperature was and what the resistance was at that time. Okay, so obviously a quantitative one is better because you can give specific values and back up your conclusions with that data. Now, in the same way with the light bulb, what kind of things do you want to make clear? You want to make sure that the light bulb is the same distance from the LDR. If you moved it around or you weren't sure where, let's say you did the experiment, you started it on Monday, you finished it on Tuesday, you didn't keep track of the distance between the light bulb and the LDR, then your results are going to be all off. So this is something you want to write about if you're explaining how to investigate this experiment. And you're going to keep that the same. Or, in fact, you could change it. You could keep the brightness of the light bulb the same and move it closer or further away. Of course, if it's closer, then it's going to be brighter. And if it's further away, it's going to be dimmer. So you're doing the same thing. You're going to measure. So you could, for example, measure the distance. Again, it's going to be voltage, current, and resistance. Voltage, current, resistance. You'll calculate the resistance each time. And this could be the distance from the resistor. Alternatively, you could measure the brightness directly. Brightness. But in that case, you would need some sort of brightness meter, or sometimes it's called a luminosity meter. And you'd maybe put that near to the LDR, and that would be just measuring. That would be measuring what brightness of light is the LDR currently receiving. And then as you change the brightness of the light bulb or move it away and closer, you can record what that was and record what the voltage is and the current is. Okay? So let's have a look. Let's go a little bit further then. In both these situations, make sure the lamp, this is again just explaining the method, so pretty much everything I've just said. It's telling you how to wire it up, which I've talked about also. Making sure that it does say to add to a power supply with a low voltage, because otherwise it might be dangerous. The components could overheat, and that would be dangerous. So it hasn't actually in here talked about what the results would be. I've explained that bit. I will talk about one other thing, which is unrelated to this particular subtopic section. And that is how we can use these components to do something that we might want to do. So this is a little bit more advanced, but let's see if we can work it out. So we've got a battery or a power supply. And what we're going to do this time is we're going to have two resistors. Well, one's going to be a regular resistor. One's going to be either an LDR or a thermistor. So, okay, so let me think about this. I'm going to, let's put the thermistor. We'll do it with the thermistor for the moment, like that. And then I'm going to make this like a sort of output voltage. Now, so that's going to be R1, that's going to be R2, and this is the voltage in, or let's just say this is the total voltage, and this is R1 and this is R2. Remember that the voltage. Let's do this first. So imagine I measured it. I know. I'll do that, and I can pick it up. So only it's a slightly wonky. I've drawn my diagram slightly wonky. So remember that in series, the voltage across this plus the voltage across that will be equal to the voltage up here. So in other words, the total voltage, well, let's just say V1 first, voltage across this, plus the voltage across this one will be equal to the total voltage. Okay. Now also, the voltage is equal to the current times the resistance. This would mean that as I increase the resistance, the voltage will increase. Okay, so I'm going to ask a couple of questions. We'll have the answers. I'll get you to answer send the answers on the direct chat, and let's also mark them as we go, and we'll add them to the mark book. I'll ask the questions on the video actually, so you can always, when you rewatch this video, it will be useful. So the first question is, what would happen to R1 when the temperature increases? All right, yes, the temperature decreases, as we said over here. As the temperature goes up, the resistance decreases. Next question, what happens to resistance 2 as the temperature increases? If we look at this symbol here, it is a symbol for a fixed resistor, which I talked about over there. So the resistance does not change. Okay, hang on a second. I just remembered I did also say, though, a regular resistance. Okay, that one, okay, I'll let you also have it if you said a resistance increases. That's a bit of a tricky one. I will say, though, in an exam, you should say it stays the same because it does, but it doesn't. Like, it if you increase the temperature a lot, it does actually. And actually, I did state that earlier on, which is why I've let you off saying it increases. Because it does increase actually, but it's not until it gets really hot that becomes noticeable. So whereas thermistors, their resistance decreases and it happens pretty quickly, so it's a noticeable effect immediately. Okay, next. So that's question 2. Question 3. What happens to the voltage V1 basically? So the voltage across the resistance 1 when it gets hotter. So you've already said what happens to the resistance across R1 when it gets hotter. What happens to the voltage across R1 when it gets hotter? Okay, so that's the next question. The voltage across R1 increases. Now, that's because a number of different ways we can say why it is. Well, 2 main ways I can think of. As we can see, the voltage is equal to the current times the resistance. So mathematically, you might be able to see that if the resistance increases, then the voltage is going to increase. If voltage is equal to something multiplied by something, this something, if it increases, then the voltage is also going to increase. In terms of just the physics, however, you could also see the voltage is going to increase because, remember, it's the difference in energy per charge between 2 points. If the resistance is higher, then more energy will be used up to go through it. So when let's say when the charge comes up to here, the charge is going to lose more more energy to go through it, which means therefore it's an increase in voltage. Voltage is the difference in energy per charge. So there's a greater difference in energy per charge if there's a higher resistance. Okay, so the answer was the voltage is going to increase across R1. That was question 3. Question 4, and this one I'll give you a whole minute to answer because it's a little bit trickier. Question 4 is what's going to happen to the voltage across R2 when the temperature increases? So what's going to happen to the voltage across R2 when the temperature increases? And 1 mark for saying the correct answer. It increases, decreases, or stays the same. And we'll say 1 other mark for explaining the reason. Okay, this is a 2-mark question. Don't forget that the voltage total will stay the same. Okay. So as the temperature increases, oh wait a second. Sorry, I just realised I messed up the previous question. As the temperature increases, R1 is going to go down, which means that the voltage 1 goes down. Okay. So sorry, I'm gonna give you another minute or something to answer this. So answer voltage 2. Okay. So now that I've gone over that bit, I'll give you 1 more minute. What's going to happen to voltage 2 as the light bulb? Sorry, as the temperature increases. Okay. All right. Good. So the answer is it increases. Okay. Now this could be misleading. A lot of people say it stays the same because the resistance stays the same. But the thing is, the total voltage across both of them must stay the same because whatever voltage I put in, which is being kept constant, must be used up on both of these resistances. Now, if we're having a lower voltage being across this resistor because the resistance decreased, then there would have to be a higher voltage across this one. V2 is equal to V total take away V1. And this time V1 is a smaller voltage, so I'm minusing a smaller amount of volts from the total, so therefore V2 increases. Now you all got that mark. I would say, Casti, you can give yourself an extra mark because your explanation essentially gets the point, all right? So if you want to just add up your score and add that to the mark book, I will give it a name, okay?